All right. In the meantime, we'll bring back the we'll bring in a new thing, which is called the multiplication rule. This is another that will be given on the formula sheet. This is probably the least likely rule for you to use on the test, but it's one that we're going to be using as part of a diagram we're going to do later, so we'll see it again. And again, the most important thing in terms of using these formulas is correctly translating what you're given and what you're looking for in the question stem. So what I want you to do is, if you look at this question, just glancing, we have 3 given probabilities and 1 probability that we're looking for. So I want you to pause the video and figure out what things go inside of these probability notations. What is the 60%? What is the 78%? What is the 65%? And what is it we're looking for? Because as I said, this is the crucial thing. If you can do this, you can use the given formulas and life is fairly easy. So pause the video, fill these out. All right, so you should be coming back. The way I would do this is I'd read through the whole thing first and sort of be on the lookout for those events. So it becomes clear that we have adopted and mutt, right? These are the things that we're going on and on about. Okay, adopted and mutt. And we can see some keywords. We have and right here, so this one was easy. We could go up. 65%, nothing about adopted in this entire sentence, right? So that 65% is fairly easy. Same thing with this first piece, that first sentence, nothing about being mutts or not, so just 60% is adopted. And then the hardest part of the piece that is the most crucial, like I said, because the order matters for the conditionals, is this last one. We have adopted, we have mutt, we do not have an and or an or between them. So we need to look a little closer. Our keyword for the last one is of. So we know the dog was adopted. Of adopted dogs, 78% were mutts. So there's all of our given information. I don't like how big that is. Right, there's all of our given information. And that's exactly what this rule gives us, right? The probability of A and B, except for we have an M. So the first thing I would do is rewrite this formula, but change all of the B's to M's. Now, next thing I usually do is plug in. I have the probability of M, that's 65, but I don't have this probability. As I was saying, it really matters what the order is. So this is different. Now I'm putting parentheses around this just for multiplication, not because I'm using the probability notation. So this right here is a problem. And what we're going to have to recognize is that while the order matters a lot on the conditional, while the order matters for a conditional, it doesn't matter for and or. Because remember, if we're thinking about the Venn diagram, and is the area between. So I don't care if it's an adopted dog and a mutt, or if it's a mutt and an adopted dog, those mean the exact same thing. Same thing for or. Now I'm filling everything, and it doesn't really matter which order I write the two things. Black and green eyes is the same as green and black eyes. No, but you get what I'm saying, minus that craziness. Green eyes and black fur is the same as black fur and green eyes. So I can change this order, and in fact, I should have just used this to begin with. And the only thing I need to know in the notation is that whatever's behind the line is the thing that we're multiplying by itself. So this formula I do have all the pieces for. And now I can plug in. This is 0.78. And again, I'm just using the parentheses for multiplication, not because I'm using any notation stuff. And 0.6. So I put this exact question on tests many times. And students always do some crazy stuff instead of whatever they're supposed to do. In fact, the crazy stuff they normally do is what's coming up next. The multiplication rule for independent events. If two events are independent, this becomes a lot easier because as we remember, knowing, so if we say A given B, knowing B doesn't actually give us any more information about A, so this is just the probability of A. So that formula from above Well, this thing just simplifies the probability of A times the probability of B. This will not be given. The reason I don't give it is because people want to use it, students want to use it all the time, even when our events are dependent. So I really want to make sure that we do not use this inappropriately. So the only time you should use this is if I tell you things are independent or you've proven it to yourself that things are independent. So do not just use this rule. But if you see the word independent, chances are we should be grabbing this. So you need to see the word independent, and then you're going, oh, sweet, let me try out that sweet, sweet rule. So let's see the example for that. 20% of SDSU students take Stat 119, and 40% graduate in 4 years. If these events are independent, what is the probability that a randomly selected SDSU student has taken Stat 119 or will graduate in 4 years? So again, feel free to read through these once as a skim, try to think of what your events might be, and then come back and see what we've got. So if we break things down, we've got a 20%, but this is about taking Stats 119. We have a 40%. Sorry, I hate when things pop up. And that's about whether or not they will graduate in 4 years. By the way, the graduation rate is not that bad. It's just that the classes are really impacted. So most students take more than 4 years to get through. And then we have the fact that we're looking for Stat 119 or graduate. And you can see I can even underline or circle my keyword. And then I underlined the word independent because as a student, the first thing I think when I see the word independent is ha. That's the first time I get to use, or that's when I have the okay to use, the sweet rule that tells me and is just the two probabilities multiplied together. Now here's one mistake already, is I could figure out the probability of S and G. I could multiply the 0.2 and the 0.4, get 0.08. And a lot of students would stop here because they've got something, but we're looking for OR. So this is when we have to go back to all the OR formulas. And if you remember, the OR formula was take the two probabilities, add them together, and then subtract off our AND probability. So in this case, 0.2, 0.4 minus 0.08. Got a 0.52. All right, so the last thing we can do with our conditional probabilities and this independent idea is that we can test to see if two variables are independent. Just as a heads up, this is a mathematical test for independence. We will get a statistical one later because we'll see some examples where 0.456 is really dang close to 0.46, but since we're in math land in part 4, they're not the same. We can say they are not independent. But when we get into stats land in like part 9, we're going to see that sure enough, there's a, well, it's close. Is it so close that they could possibly be independent? And we'll have a better frame of reference. So anyways, both the formulas that we've seen are good ways to test for independence. We could use this rule, or we could use that given notation we saw already in use when we were playing with the dice.